Thank you very much, Giovanni. And that is now actually a nice bridge from the more static properties we have seen in Helen's talk to the dynamics. And I will go to the ultimate limit, which is the Bose-Einstein condensation, because the Bose-Einstein condensate is really a state of new matter. So it's not only just an excitation of a system. So let me show you what I would like to produce here, but now I have to get it working. Okay, so we start with the magnons, and we can think magnons as, of course, dynamics, but we can also think of magnons as particles, particle-wave dualism. And if you think in terms of particles, then each magnon has energy, like you see here, essentially given by the frequency. It has linear momentum, it has mass, it has spin in particular. And what is particular about this very specific system is that magnons are nonlinear objects. So they have nonlinear scattering, and most important is the 4 and the 3 magnon scattering mechanisms. That makes it different, for instance, from optics and also from phonons, because, you know, in the latter two systems, it is very hard to achieve nonlinear phenomena. In optics, for instance, the Maxwell equations are linear, and you need to have a nonlinear medium, and you all know how difficult that is to achieve. I mentioned already Bose-Einstein condensation. So just a very quick tour what I mean here. You all know about the Bose-Einstein distribution function, and you find it actually here. You have the density of the Magnon states, and then you would like to know what is the occupation. And essentially it's a factor here in the denominator, and it contains the temperature, because we're talking thermodynamics. It contains the energy of a Magnon, so the h bar omega. And it also has a chemical potential. If you think about gases, and we'll come back to gases in a minute, then normally a gas which is just the air around us doesn't have a chemical potential because it is an open system. But we can manipulate the chemical potential very nicely, and you will see in a few seconds how this works. If we close the system and then we just inject magnons from outside by certain means. So we can actually produce a change in the chemical potential. Let's just look how it looks like. What I plotted here is the quasi-particle density, so it's this parameter rho, as a function of the frequency in a double logarithmic scheme. And if you have a given temperature, and if you have an open system, so no chemical potential, we typically get here is this green curve. What is specific is there is a frequency, there is a minimum frequency. You would see that is because of the dipolar interaction. Magnons always have a minimum frequency. And then we can ask ourselves what happens if we now increase the chemical potential. For instance, we could make it equal to h bar omega, and then already from this equation you can easily find out what happens. This difference here becomes 0, so the exponential term becomes unity, and unity minus the other unity in the denominator again gives 0. So in other words, the quasi-particle density will diverge. And you see it here schematically shown with this green curve. And this we consider a very important fingerprint of a Bose-Einstein condensate. It's not a proof, but it is a very strong fingerprint of Bose-Einstein condensation. Okay. Why I am advertising so much these Bose-Einstein condensates here? Because I find that it could be used for computing in the future, and I will show you some ideas how this could actually happen. Also, I will mostly focus on the properties of these condensates now on the nanoscale. But just looking at the computer background, we have classical computing, like you do with your own computer. So in your own computer, you have electrons, and they carry the Boolean bits, and you have Boolean logics inside. You also know that you can use wave-based computing, which sometimes has many, many advantages. You have additionally interference in your system, which you don't have in your computer. There is no real interference. But if you have wave, you can get interference, so you get 4 times the intensity if you have constructive interference of the contributing waves. And you can continue to think along these lines, and at the very end, you end up with something which is very much now in the public domain nowadays, which is quantum computing, where in addition to the waves, because in quantum computing we discuss wave functions, you also have properties such as the entanglement. And the question is simply, is there anything in between which could be very, very useful? And yes, there is, and I would like to advertise this at the macroscopic quantum state computing. The idea is very simple. If you go down here the scale, there is one parameter which increases, and that is a parameter something like the coherence length. If you look classical computer, you only have the Berkeley wavelengths, and the coherence length is very short. If you make waves, like optical waves, you know the coherence length can be long. If you have a macroscopic quantum state, that state is defined by the coherence length, because it simply defines how big your state object is, which you would like to use for certain applications. And of course, coherency plays a very important role in quantum computing, as you all know. So you can simply think about the schemes as a performance you can achieve. And that is, of course, that what you essentially would like to buy in a shop if you have a computer. That increases if you just increase here the concepts you are using for computing. So many words for the background. Now let's go back. It was meant to advertise that macroscopic quantum states are extremely useful. And the main idea is now to find macroscopic magnonic quantum states, which we can use for information transfer and also for information processing. And if you look back into the history in physics, you know very well these things exist. For instance, we have superconductivity, we have Josephson currents, we have superfluidity, and these transport mechanisms even can be free of dissipation, which is very, very useful, for instance, if you talk about energy transfer. But you also know the problems, because this all exists only at very low temperatures, at least so far as it is available on a semi-commercial level. What I now would like to talk about is the macroscopic magnonic quantum states in confined systems. So that is, this connection is the new part. And I can already tell here that we are not confined anymore to low temperature. So if I like to use the saying, if I would like to have a quantum computer in my wristwatch, we cannot do it in the conventional technology, because you cannot have a fridge in your wristwatch. But if you have a mechanism how to copy these kind of things into a system which operates at room temperature, then of course you gain a lot of advantage. And maybe the magnons and magnonic quantum states will do exactly this job. That is why I see the big potential behind this kind of research. Just a definition. Why do we name this a macroscopic quantum state? So what is the relevant length scale? So just this view graph on this. If you look at the microscopic scale, then we have the wave-particle dualism. That is what I started my talk with. And this simply says that the microscopic scale of the system is comparable with the Berkeley wavelengths of a particle. So if you do it with electrons, for instance, what matters for interference of electrons is the Berkeley wavelengths of the electrons. Same for the Bose atoms in Bose-Einstein condensation at ultra-low temperatures. If we would like to go to the macroscopic world, so the macroscopic quantum phenomena, then it's not the Berkeley wavelengths anymore. It is now the coherence lengths you can achieve. And in order to achieve a large coherence lengths, we have to go to the macroscopic quantum states. And the best-known systems are the Bose-Einstein condensates of particles, where we have a spontaneous population by a large number of Bose particles, which all go into a single quantum state, which then develops macroscopically large coherence lengths. And here I will discuss with you the BEC of magnons, the quanta of the spin waves. And again, we get a large coherence length, and important is it is a quantum mechanical transition. So we have a spontaneous formation of the coherent wave out of an otherwise chaotic Magnon system. Actually, the question is always, is this now quantum or is this classical physics? The answer lies in the description, which is most convenient here, by the Gross-Bitaevsky equation for the Berkeley waves or for the spin waves. And it has a lot of classical properties, but of course there is also quantum mechanics in it. For instance, if you look to the very famous Josephson effect of electrons, that is a purely classical effect. You can describe it in purely classical terms, as already has been shown in the 70s, if and only if you form Cooper pairs out of the electrons, and the Cooper pair forming mechanism, of course, is a quantum mechanical mechanism. So properties of both types of condensates are almost identical, and that is why we talk about quantum macroscopic quantum phenomena, and we make use of the analogy which already was mentioning here. And I should say already in magnonics we have supercurrents, we have Bogoliubov waves, we have the Josephson, the alternating current Josephson effect. So all these kind of things exist in the magnonic world. Now, one application which we are considering at the moment, so that is now hot research in my group in Kaiserslautern, it's very simple. If we do Bose-Einstein condensation in a magnonic system, and what you see here very schematically is just the dispersion properties for a magnonic system, very, very schematically. So here with zero wave vector, we plot the energy as a function of the wave vector, and then you see we have modes which go through a minimum at finite wave vector and then they go up. It's called the backward volume modes for the exports, or we have other modes which directly increase here, like the surface modes. And we have any modes here in between because we work with thin films and there are all these standing waves in these films. So essentially, what we have is just a continuum of modes. If the film thickness is large, or this gray area. And now if we do the things right, we can get a condensation here at a minimum frequency at a finite wave vector. And since the system is reversible with regard to the wave vector, we get two of these minima. And what we are considering at the moment is simply that such a condensate of magnons can be very useful for quantum computing, because what we have here is a qubit, a magnonic qubit, because we can define our Bloch sphere with the north pole defined here by the Bose-Einstein condensate at positive wave vector, and the south pole as the Bose-Einstein condensate at negative wave vector. These are coherent objects, so we can discuss any kind of coherent superposition. So that means any other point here in between. And we have all the ingredients what you need for a qubit, like you need in quantum computing. We're still in the classical world, apart from the mechanism which leads here to the quantum particles. So you see the potential behind, and we have already shown in not yet is this unpublished work, and I have no time to go deeper into this, but we have shown by numerical simulation that we can manipulate this qubit state, that we can have two qubits interact, and that we can get the logic functionality which you have in quantum computing. Okay. But before going more into this, we have to do some more homework, because we need to understand the processes we have here. And what we do is, first of all, we need to prepare the system. And I will show you now two mechanisms how this works. One mechanism is a very old one, which goes 14 years back when we first have shown it. That is just pumping the system with parametric pumping. Parametric pumping is a very simple process. We have a microwave photon. The microwave photon decays into two magnons of opposite wave vector, half the frequency, because we have energy momentum conservation. And then these magnon states here at this violet frequency, at this pink frequency, are populated. And then we take advantage of the nonlinearity of the system, because if we populate these states here, they undergo four-magnon scattering. Four-magnon scattering simply means we have two green magnons, incoming magnons, they scatter, and the outgoing magnons are designated here with a blue color, so two magnons go out. And this happens with energy, momentum conservation, very much like a normal gas. If you think about the air surrounding you, all these gas molecules scatter because two gas molecules just hit each other, and two gas molecules are scattered. Again, four particles are involved. And in this gas scattering events, again, the energy and the momentum is conserved. So we have the same thing here in this scenario, and that is why we like to call this a Magnon gas. And now, in your way of thinking, you can simply just move down with all the classical idea you have learned in the first and second class of physics. and that is you have evaporative cooling. Yeah, the same way like your coffee cools down if you let it sit too long on your desk. Also, this Magnon system cooled down by evaporating magnons up to higher energies, so that eventually all the magnons can condense here in the Bose-Einstein condensate state. So that is the idea behind. So generation simply by bringing an imbalance into the system by parametric pumping, and this works very, very, very well. You can think about it in a different way, that you throw these magnons into the system so fast that the system cannot relax the normal pathway, and the only way for the system to escape this in equilibrium situation is to form the Bose-Einstein condensate. And if you like to think about that, you can ask yourself, if you bring the system so that the magnons cannot relax the usual way in order, and they form the finite chemical potential, are there other ways how to do this? And yes, there are. What you have seen here is, if you like, there is some kind of spatial pumping, because we bring the magnons all here in the state, and then at that location the magnons will condense by exchanging energy and momentum with each other. But we can also generate such an imbalance by working on the time scale. And the idea here simply is that we take such a system and we cool it ultra fast, so fast that the system cannot relax in the usual manner, or in other ways, the cooling rate is much, 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 much faster than the usual relaxation rate of the magnons. And indeed, this works very, very well. And what I would now like to show you is something which mostly has been done by Andrei Chumak, who now moved to the University of Vienna, and Michael Schneider was a PhD, or still is a PhD student, who has done all the work, and Alexander Salga was also largely involved here in this work. And what we brought together is Andrei Chumak's very special expertise in making these magnetic nanostructures out of yttrium iron garnet, and our competence in this Bose-Einstein condensation. So the idea is very simple. You have seen this figure before, just the distribution function of the magnons. Here the quasi-particle density as a function of frequency, and this is plotted for a finite temperature, let's say room temperature, no chemical potential. And now we can heat up the system. That is the same system at a somewhat larger temperature. If the temperature is higher, you see T is here in the denominator of the exponential term. Simply the population is higher. Higher temperature simply means more magnons are excited in thermal equilibrium. And now what we can do is we can ultra rapidly cool down the system, and then we have a problem, because if you bring the system back to the original temperature T min, then all these magnons here in the shaded area are now suddenly excess magnons, and the system needs to get rid of these magnons because they are just not in thermal equilibrium. And then we can ask ourselves, what are the mechanisms behind this? And number one, we have always the damping to the phonons, the Gilbert damping, which is more effective for larger frequencies. So you see already this will lead to an imbalance here in the curve. But we also have the four-magnon scattering processes. And we also have other processes like Cherenkov scattering, which is scattering of magnons with phonons. No time to go into the details. But essentially what these processes do, they transport the center of mass of this distribution to lower frequencies, to lower energies. And if you do everything right, that is now a result of numerical simulations, then we see again the system escapes this inequilibrium situation by developing a Bose-Einstein condensate, and here simply showing up as a divergence here in this green curve. And you see this happens if the chemical potential is equal to the minimum frequency here in the dispersion curve. So that is very, very important to memorize it. Here is the experiment which Andrei and Michael have performed. What they use is a stripe of YIG, which is just the central part here, on a large, thick GGG substrate. GGG is actually a very good thermal conductor, which is very helpful here. Then we need to heat up the system. That is done by putting a platinum overlayer. Platinum only is used here as a heater, so no spin transfer. And here are the contacts to put electrical currents through it. And then we can use Brillouin light scattering to measure the Magnon population. So everything is very small. You see this here, the YIG film signal is 70 nanometers, and the width here is only 500 nanometers. So that is pretty demanding to make this kind of structures. Okay, this experiment cannot be done. And I show you here what happens. We start, I have to look at both pictures. You have seen this picture here before. So we start at room temperature, and then we can measure the spin waves or the Magnon distribution in the system, that is frequency. We get a couple of modes which we do understand very well. There is a fundamental mode where later on the Bose-Einstein condensate will develop. We also get a perpendicular standing spin wave, which is discrete because of the finite thickness, all well known to the experts, and it doesn't really so much matter here. You only need to know there are these discrete modes. There's also an edge mode, which exists at the edge of the film, also a known phenomenon. Now we can put a DC current through the platinum, then the system heats up. You see that the standing spin wave just simply goes down here. That is because of the heating, the saturation magnetization is reduced. So this can all be very well understood. But now, if we suddenly stop the heating, then immediately all the heat will go to the substrate. And what we see here in the color map is that we suddenly get a very high intensity. Red color here is the color scheme. Red color simply means very, very high density. And that is exactly what we were expecting, because now we see the characteristic divergence here in the quasi-particle density. So that is very nice. So we see the expected fingerprint of a Bose-Einstein condensate. Is it a Bose-Einstein condensate? Of course, that is not a proof. That is only a very strong hint. And I will now show you an even stronger hint that this is really the case. And why is this not moving now? Let's see. Okay. And this I will show you by simply measuring now the chemical potential. The good thing here is we have discrete modes, and we can calculate the chemical potential from the imbalance of the populations of the fundamental mode and the next higher mode, which is excited in the system, which in this case is the first perpendicular standing spin wave. Any other mode would equally do well. So if we measure the population, then we can calculate here this ratio, which gives us directly the chemical potential, assuming a Rayleigh Jeans distribution, which is the same like the Bose-Einstein distribution in the classic limit. Is there an issue? I hear some noise.
No, someone go in just with the microphone unmute, so it's okay.
Okay, fine. So now this is a semi-proof. Let's measure the chemical potential, and here is the result. So we can calculate from the experimental data the chemical potential. There is no fit parameter. And what you see here as a function of time now is number one here, the frequency, or if you like, the energy of this fundamental mode where the Bose-Einstein condensate develops. And here's the chemical potential. And you see exactly here where we observe the divergence, we now see here very nicely that the chemical potential touches the energy of this mode, and therefore we see the divergence. I think I couldn't think about a better proof apart from the other proof which has been made in the group of Sergei Demokritov, who has directly shown the coherency via an interference experiment some time ago. So for these nanostructures, obviously Bose-Einstein condensate exists. And you don't need very much. You just need the sample. You need a pulsed heater. And of course, you need a means how to observe the condensate. But in principle, that is a very simple condensate. Is it really true? Well, there is a very nice tool which we also have seen in Helena's talks, that is that we can do numerical simulation, and that is now particularly the work of Morteza Mohseni, a PhD student who just finished his PhD, and Philip, a senior scientist in my group, was largely involved, and we collaborated also with Arne Bratasch, who has helped us a lot with his background in numerical simulation. Idea is very simple. We simply take the system we have onto a computer, so a YIG stripe. here a microwave antenna. In this case, we use parametric excitation, and then we can excite these modes here. And now a pure computer experiment. If we do so, if we switch on the microwaves and wait a little bit, very shortly, we see that indeed these states here are populated. And now we can really monitor where it happens. You see a lot of population here, a little bit here farther out on these branches. These are, again, here the fundamental mode and then the higher order standing spin waves. And now we know there is a four-magnon scattering. There's a threshold which has to be overcome. And if we wait a little bit and use the right amount of intensity, then we see very nicely how now these states undergo four-magnon scatterings. Some modes go up, others go down. You see here some discrete modes. And now, if it takes this data and wait a little bit, then after some time, we see how nicely now the Bose-Einstein condensates develops in this computer experiment. And the parameters in this computer experiment are very close to the experiment, so we can really now follow our experiment with this parallel computer simulation. Just to show you that it works, there's one more view graph. That is, we can measure the spin wave amplitudes. So that is a parametrically measured amplitudes measured in the computer experiment. Here is the condensate, and here are the corresponding thresholds which you find. We find a threshold for the condensate. We find a threshold for the four-magnon scattering, and here is a threshold for the parametrically generated magnons. So first you generate the parametrically generated magnons, and then the four-magnon scattering sets in, and finally the condensate sets in. So these numerical simulations now allow us really to monitor in every detail the process which is going on here. Here is an experiment we have done, just the same experiment, the nanostructure, 85 nanometer thickness, 500 nanometer wide, and in the structure we see the same thing like you have seen in the numerical simulation. Characteristic peak here, which we get after switching off the bumping of the Bose-Einstein condensate, and the characteristic two-step decay here. Okay, my time is up. I should summarize. I reported the first experimental evidence that a Magnon BEC can be generated by the rapid cooling process. You have to cool faster than the system can relax. The injection mechanism originally is incoherent, and it can be applied to any bosonic system. And of course, the condensate itself is coherent at the very end. So Magnon condensation in microconduits has been demonstrated by us, and we can confirm that by micromagnetic simulation. And we also have confirmed it by the first experimental investigations. So the outlook, this of course now opens many new directions. And what I find most exciting at the moment is the experiment which I described, as sketched at the very beginning, is making now qubits out of this and use all the different means we have to manipulate these qubits. That is ongoing research now. Spin transport, I could not discuss it, can be done using Magnon supercurrents and Bogoliubov waves. And computing with these two component Magnon condensates is now really where I see the big future for that. Thank you very much for your attention.